Welcome to part 1 of the fundamental theorem of line integrals. The fundamental theorem of line integrals, as stated here, states that if a vector field is conservative, then the line integral between any two points forming curve C is the difference in the values of the potential function little f at these 2 points, regardless of the path. So the line integral would be path independent. And this is also sometimes called the gradient theorem. So now, to evaluate a line integral, we have a choice of methods. This first method here requires us to parameterize the curve in terms of t, rewrite the vector field in terms of t, dot it with r prime of t, and integrate with respects to t. And this method does not require the potential function. However, if c is conservative, and we can easily determine the potential function, we could take advantage of the fundamental theorem of line integrals. The third option is, if f is conservative, we could use method 1, but use a much simpler path because we know that if f is conservative, the path would be independent. So in this video, we'll take a look at one example and evaluate the line integral using all three of these methods. And we'll start by using the fundamental theorem of line integrals. So first we'll check to make sure this is a conservative vector field. Since this is a vector field in R2, we have to check to make sure that the partial derivative of g with respects to x is equal to the partial derivative of f with respects to y, where f would be xy squared and g would be x squared y. Well, the partial derivative of g with respects to x would be 2xy, and the partial derivative of f with respects to y would also be 2xy. So this is a conservative vector field. So the next step is to determine the potential function so we can determine the value of this line integral. Since f is conservative, we know that the vector field f is equal to the gradient of little f. So this tells us the partial derivative of f with respects to x would be xy squared, and the partial derivative of f with respects to y would be x squared y. So now we'll integrate xy squared with respects to x, and then integrate x squared y with respects to y. And by comparing these two antiderivatives, we can determine the potential function. So here we're going to have 1/2 x squared y squared plus a function of y. And integrating with respects to y, we're going to have the same thing, plus a possible function of x. But since these are equal to each other, we can conclude that the potential function f of x, y would be equal to 1/2 x squared y squared plus a constant c. So we can use this function to evaluate the line integral. So let's do that on the next page. So before we evaluate this, let's take a look at our path. We start at the origin, or the point 0, 0, and we finish at the point 3, 3. And these are the only 2 points we need to determine the value of this line integral. This is going to be equal to f of 3, 3 minus f of 0, 0. Replacing x and y with 3, we'll have 1/2 times 3 squared times 3 squared minus, and then when x and y are 0, this would be 0. So we have 9 times 9, that's 81 times 1/2, or 81 halves. So using the fundamental theorem of line integrals, we were able to determine the value of this line integral using the potential function. So we just used method 2. And now what we're going to do is use method 3, where we know f is conservative, but now we can define a simpler path and then use method 1, where we parameterize everything in terms of t. So looking at our path here, a simpler path would just be the line from the origin to the point 3, 3. So we'll use this path instead of the blue path. And knowing the equation of this line would be y equals x is going to be helpful. So if we let x equal t and y equal t, then t would be on the closed interval from 0 to 3. Now we can rewrite our line integral in terms of t. T is going to go from 0 to 3. F written in terms of t would be t cubed and t cubed. And r prime of t would be 1, 1. So we're going to have t cubed plus t cubed, or 2t cubed. Integrating with respect to t, we're going to have 2 times t to the fourth over 4. That'll give us 1/2 t to the fourth. So when t is 3, we'll have 1/2 times 3 to the fourth, which of course is also 81/2. Here we didn't use the fundamental theorem of line integrals, but we did take advantage of knowing that the vector field was conservative and therefore path independent, meaning we could redefine the path. Now let's take a look at the same problem using the original technique for integrating line integrals. So we have two paths to consider, path 1 and path 2. The equation of curve 1 would be y equals 3/2 x, and the equation for curve 2 would be y equals 3. So let's go ahead and parameterize our curve in terms of t. So for curve 1, if we let x equal t and y equal 3/2 t, and t would be on the closed interval from 0 to 2. And for the second curve, x starts at 2 and goes to 3, so if we let x equal t, and the interval for t would be from 2 to 3, that works perfectly, and the y component would stay constant at 3. So because we have two curves, we have to set up two integrals in terms of t. We're first going to have t from 0 to 2, where x y squared would be t times the quantity 3/2 t squared. That'll be 9/4 t to the third. And then x squared y would be t squared times 3/2 t, or 3/2 t cubed. Dotted with r prime of t, that would be 1 3/2. Integrate with respect to t. And our second integral is going to be from 2 to 3, where x y squared would be 9t, and x squared y would be 3t squared. And our prime of t would be 1 0. So as you can see, the original method in this problem is going to take a lot more work than the previous two methods. Let's go ahead and finish this on the next page. Okay, so here we're going to have 9/4 t cubed plus another 9/4 t cubed. It'll be 18/4 or 9/2 t cubed. Here we'll just have 9t. So we'll have 9/2 times t to the fourth over 4. Here we'll have 9 times t squared over 2. So replacing t with 2, we're going to have 16 divided by 4, that's 4. 4 times 9/2, that's going to be 18. And then when t is 0, we'll have 0. Over here, when t is 3, we'll have 81/2. And then when t is 2, we'll have 18. So notice the 18 simplify out, and the final result is also 81/2. So hopefully now you see the advantage of using the fundamental theorem of line integrals when you know the vector field is conservative. In part 2, we'll take a look at some more examples just using the fundamental theorem of line integrals. Thank you for watching.